Okay, so let's go back to that notation that I was using in the last couple clips. So suppose I say that x is equal to, and then we've got curly bracket a, b, c, like that. Okay, so the meaning of this then is that x is a set, and that, so this guy is a set, and these guys here are elements. And by the fact that they're things that belong to the set X. And the fact that there's nothing else listed in there means that X is just a set with three things. And so we might describe a set by explicitly listing all of the elements of it, or we could give some kind of a description. So I might say, here, let's let Y be the set of all 3x3 matrices. Okay. And then sometimes to facilitate the description of a set, it's nice to specify things that have a certain property or satisfy a certain condition. So let's let E be, and I'm going to say, it's all of the things Z, which are elements of R. So in other words, it's consists of real numbers. So that is the class or type of object that lives in our set. And it's going to be those ones such that they satisfy some condition. So I'm going to say Z needs to be equal to 2 times n, where n is an integer. Okay, so here we've got satisfying this mysterious condition. Okay, so we're looking at all real numbers that can be written as 2 times a whole number. And so if you haven't seen it before, this symbol right here, that's the symbol for the set of all integers. And if you're wondering why we should use Z for integers, it's because it comes from the German word Zahlen, which means number. Okay. So E. So why did I call this set E? Well, this is the set of even numbers. So the set of even integers. Okay, so this is called set constructor notation. Not that you'll ever need to remember this for the rest of your life, but that's just this idea where you say, okay, it's going to be all things of this type that satisfy this criterion. Anything satisfying that criterion is in there, and if you're in there, then you have to satisfy that criterion. Okay. Let's see. So what's another example? So I could say like S. Let's take S to be all the elements of Y. So that is all the 3x3 matrices, such that if I take a transpose, I get a back again. And so here we're looking at something where the type is 3x3 matrices, and the condition is that they should be symmetric. Okay, so not all 3x3 matrices, just the symmetric ones. Okay, so that's another example here. So there's an example. There's an example these are examples of sets. And then it's also possible to write these in a slightly different way using an indexing notation. So let me take this example for the evens down here and do like a little alternate version of it. I could say that E is the set of all things of the form 2n, where n is an integer. Or if you like, it's the set of all things of the form 2n, where n runs through the integers. And so from your calculus courses, you might have seen notation that looks a little bit more like this for describing sequences, or when you studied series and stuff like that. Okay, so the example that I gave you in a previous clip was that the complex numbers looks like all thingies of the form a plus bi, so all numbers of the form a plus bi, such that a and b are real numbers. And depending on the context, may or may not include the fact that I is defined like this. Okay, so that is sets. Okay, so those are sets. Now let's talk about lists. Okay, so a list is going to be denoted by round brackets instead of curly brackets. And we often number the entries. So we might have something like x1, x2, or y1, y2, y3. And this is the notation we'll use for talking about vectors. And so here, depending on the number of entries, we might refer to it as a pair or a triple, or if there's n of them, maybe an n-tuple. So since we don't have special words like pair and triple, I guess we've got quadruple and quintuple, but eventually it just becomes obnoxious. So just call them n-tuples for anything bigger than 2 or 3. And implicit in this is that we're talking about a situation where order matters. And typically I won't actually bother to say the fact that it's ordered, that's just implied. But the idea about order matters is that 0, 1 is not the same thing as 1, 0. And so you know that this is true in the context of where these lists represent vectors, because one of them is a point over here, and one of the other is a point over here, and these are different, right? Okay. Sometimes you see lists that go on indefinitely, in other words, forever. In other words, they're infinite. And instead of calling this an infinite n-tuple, people usually just call this a sequence. All right. I should also mention that repetitions matter. So, in other words, if I have a sequence that goes 0, 1, 0, 1, and so on forever, you know that that's a sequence that bounces back and forth between two different values, sort of 0 and 1, infinitely many times, right? As opposed to if I have a set that looks like 0, 1, 0, 1, etc., with a bunch of junk like this, well, sets don't care about repetition. They really only care about the number of distinct values that are in there. So this would be the same thing as just the set 0 and 1 by itself. However, this is not the case for lists. Okay, so that's the difference between sets and lists. And so we will be using lists as our notation for vectors.